Look at this building. 7,600 tons of concrete and steel literally walking through the city. This isn't a movie, and it's not a demolition. A few hours ago, it was stuck in the ground. Now it's gliding 62 meters across the street like a toy. Engineers across the globe swore this was physically impossible, but China just shattered the laws of modern architecture. Here's how they pulled off the impossible. For most of human history, a building was the most permanent thing you could own. You could move furniture, move cars, even move entire families across continents. But the building stayed. It was the fixed point, everything else moved around. China just erased that rule. Today, structures weighing thousands, sometimes tens of thousands of tons, are being lifted onto robotic legs, hydraulic jacks, and rolling platforms, and relocated like oversized furniture. Schools, century-old neighborhoods, bus terminals heavier than the Eiffel Tower 3 times over. None of them demolished. All of them walked, rolled, or slid to a new address. This isn't a gimmick or a one-off stunt. It's a quiet engineering revolution that started with hydraulic jacks in the 1950s and has evolved into something that looks, frankly, like science fiction. Buildings that move on their own legs. And China isn't the only place it's happened. In 1999, the Cape Hatteras Lighthouse in North Carolina, all 4,830 tons of it, was moved 2,900 feet inland to save it from coastal erosion, one of the most celebrated feats in the history of the house-moving industry. As far back as 1930, the Indiana Bell Building in Indianapolis was rotated a full 90 degrees on its foundation, without interrupting a single day of telephone service. These weren't flukes. They were proof of concept for everything that followed. England got there the same year. In 1999, the 850-ton Bell 2 lighthouse on England's south coast was nudged 17 meters inland, pushed along steel and concrete beams by 4 hydraulic jacks to escape a crumbling cliff edge. The scale was modest next to what would come later in China, but the principle was already proven. Lift a structure evenly enough, and it will travel without complaint. Let's start with the case that put this technology on the world's radar. The Lagena Primary School in Shanghai was built in 1935, during the era of the French concession. By 2020, the city needed that land for a new commercial complex, and the easy answer would have been to tear the school down. Instead, Shanghai Evolution Shift, the engineering firm behind the project, decided to move it. The problem was the building's shape. It was T-shaped, 5 stories tall, and it needed to travel along a curved path while rotating 21 degrees, something that rails or flatbeds simply can't do. Straight-line moves are one thing. A curve with a rotation, on a building that heavy, is a different category of problem entirely. So the engineers built what they called a walking machine. They dug underneath the school and installed nearly 200 mobile supports, robotic legs equipped with sensors, split into 2 groups that rose and fell like alternating footsteps. Lan Wuji, the project's chief technical supervisor, described it simply. It was like giving the building crutches so it could stand up and walk. This wasn't Evolution Shift's first attempt at moving history. 2 years earlier, in 2018, the same firm slid Shanghai's Jade Buddha Temple 31 meters along a bed of jacks and rails, a smaller dry run for everything that followed. Lan later compared the delicacy of that earlier job to carrying a full tray across a crowded room without spilling a drop. Lagena was simply the first time the company let a building walk on legs of its own instead of riding rails. After the original support pillars were cut away, the legs lifted the entire 7,600-ton structure off its foundation. Then, one careful step at a time, it began to move. Sensors on each leg fed data back to a control system, keeping the whole building level and synchronized. So the structure that was sitting on 200 independent legs moved as a single, rigid object, rather than tearing itself apart at the seams. The journey took 18 days to cover 62 meters. That's roughly 3.5 meters a day, slower than a person walking. But for an 85-year-old masonry building, that pace wasn't a limitation. It was the entire point. Speed was never the goal. Keeping every brick exactly where it belonged was. When the school reached its new site, it didn't become rubble in a landfill. It became a heritage and cultural education center, a building that survived its own relocation and kept its history intact. A textbook example of adaptive reuse, where preservation and progress share the same address. Walking legs are dramatic, but they're only the newest tool in a much older trade. Structural moving as a discipline goes back centuries, originally relying on nothing more than horses, logs, and brute patience. The real turning point came in the 1950s, when an engineer named Pete Friesen developed the unified hydraulic jacking system, a method that let crews raise a building evenly across dozens of points at once, instead of jacking it up corner by corner and hoping it didn't crack. Friesen came to the trade almost by accident. A self-taught farmer in British Columbia, he moved his first building on borrowed dollies in the late 1940s, built his own improved screw jack by 1948, and by 1955 had wired dozens of jacks into a single hydraulic circuit. One operator's hand on a valve could now raise an entire structure as if it were one solid block instead of 1,000 separate points of strain. That single invention is still the backbone of most building moves today. Picture a building in Wuzhou, in China's Guangxi province, a 16,650-ton apartment block 8 stories tall, raised off its foundation, and rolled 35 meters horizontally over 11 days. Or the Zhengguangge building in Shanghai, a 6-story brick warehouse from 1935, lifted by 28 hydraulic jacks, each capable of supporting 200 tons, then slid 38 meters along a custom track to make way for a neighborhood redevelopment. The toolkit, broadly, breaks into 3 approaches. Hydraulic jacks lift the structure off its foundation. Steel rails, rollers, or rubber-tired dollies carry the weight horizontally. And now, walking systems, like the ones used at Lagena, replace static support with active, sensor-driven legs that can handle curves and rotations rails simply cannot. What changed isn't the basic physics. Lifting something heavy and sliding it sideways is not a new idea, it's the precision. Modern relocations use real-time sensor feedback, synchronized hydraulics, and in the most advanced projects, AI-assisted control systems that adjust hundreds of support points simultaneously to keep a structure leveled down to the millimeter. Engineers also increasingly rely on building information modeling, or BIM, to simulate the entire move in a digital twin before a single jack is placed, stress testing every scenario virtually so nothing is left to chance on the day. A 1950s crew adjusted jacks by feel and experience. Today's engineers adjust them by algorithm. And that shift from craft to computation is exactly what made the next leap possible. Moving not just a single building, but an entire historic neighborhood without losing a single wall. If Lagena proved a single building could walk, Shanghai's next project proved an entire neighborhood could. In June 2025, engineers faced the Huayanli complex in Jinghan district, a cluster of 1920s and 1930s shikumen houses. The distinctive Shanghai style that blends Chinese courtyard layouts with Western townhouse facades. This wasn't one structure. It was a dense web of interconnected buildings covering over 4,000 square meters and weighing roughly 7,500 tons combined. The city needed the land underneath it. A new 3-level underground hub was planned there, connecting 3 metro lines and adding 53,000 square meters of commercial and cultural space. Demolishing Huayanli wasn't on the table. It's considered one of Shanghai's best-preserved shikumen complexes, and officials wanted it back in its original spot once construction finished underneath. So engineers deployed 432 walking robots, each one small enough to fit in your hand, yet individually strong enough to carry dozens of tons. Spread across the entire footprint of the complex, they lifted the buildings as a coordinated swarm and advanced roughly 10 meters a day, slow, deliberate, monitored constantly by sensors and computer modeling that adjusted each robot's load in real time. The conditions underneath were brutal for traditional machinery. Zhangyuan's lanes are narrow, some barely over a meter wide, lined with walls, staircases, and thresholds a bulldozer could never navigate. So alongside the walking legs, the team used specialized drilling and earth-moving robots with folding arms built specifically for those tight corridors, guided by deep learning systems trained to tell the difference between soft clay and solid obstacles underground. This is the part that separates Zhangyuan from a single walking school. It wasn't one rigid box being moved. It was a 100-year-old, irregularly shaped maze of connected buildings, and the entire swarm had to move it without a single wall cracking. China's own engineers called it the most complex relocation the country had ever attempted when you factor in weight, footprint, and density together. Tucked inside the complex sits a 1928 assembly hall that once doubled as a night school for patriotic education, a single room so historically protected that engineers built the entire robotic choreography around preserving it, rather than the other way around. When finished, the cavity beneath Huayanli will connect metro lines 2, 12, and 13, stitching 3 subway lines together directly under a neighborhood that predates the subway system by nearly a century. Once the underground hub is finished, the same robots will carry Huayanli right back to where it started. But the project that pushed this technology to its absolute limit didn't involve walking legs at all. It involved sheer scale. In Xiamen, a high-speed railway line needed to cut straight through the site of the Huaxi long-distance bus station, a structure far too new and far too valuable to simply demolish. So engineers decided to move the entire thing, all 30,000 tons of it. To put that number in perspective, that's roughly twice the weight of the Eiffel Tower, moved sideways like a piece of furniture. The technique was called structured assisted translation. 532 hydraulic jacks, combined with a network of motorized rails, every single lift and shift synchronized by a central computer program to prevent any uneven strain that could crack the structure. Put another way, it was the equivalent of parking 170 Boeing 737 jets nose to tail and sliding the entire row sideways without anyone aboard feeling a bump. Over 40 days, the building was first rotated into position, then slid 288 meters along its new path. 40 days sounds slow until you remember what's actually happening. A 30,000-ton object, larger than most stadiums, being repositioned down to fractions of a millimeter, with 532 separate jacks all moving in coordinated lockstep. When it was finished, Guinness World Record certified it as the heaviest building ever moved on rollers, a record that, as of right now, still stands. It pushed past earlier milestones that once felt unbeatable, like the 18,000-ton mansion moved in Baku, Azerbaijan, back in 2013, and the 15,000-ton Fugang building relocated in China's Guangxi province in 2004, which was itself a Guinness record at the time. Guinness actually logged 2 distinct achievements that day. Beyond heaviest building moved on rollers, the 90-degree pivot also earned the record for longest arc rotation ever performed on a pivoted building, 2 milestones inside one continuous 40-day maneuver. What the Xiamen project really demonstrates is that the limiting factor in building relocation was never really weight, it was control. Once engineers can synchronize hundreds of jacks or hundreds of robotic legs with millimeter precision, the size of the building becomes almost a secondary concern. The same logic that walks a 7,000-ton school down a street scales up with enough hardware and enough computing power to sliding a 30,000-ton terminal across an entire construction zone. And that raises an obvious question. If weight isn't really the obstacle anymore, what is? What's left isn't really an engineering question anymore. It's an economic and cultural one. Demolition has always been treated as the default, the cheap, fast option, while preservation was the expensive, complicated alternative. These projects flip that logic. Moving a building still costs money and time, but it's no longer the impossible option it used to be. It's a line item. The arithmetic backs that up. The Huaxi terminal cost roughly $39 million to build back in 2015. Moving it intact ran about $7.5 million, a fraction of what demolition, land clearance, and a brand new structure would have demanded. That changes how cities think about their own history. A historic school doesn't have to choose between standing in the way of progress and being bulldozed for it. A century-old neighborhood doesn't have to disappear just because the land underneath it has a new purpose. The building can simply step aside, let the new infrastructure go in underneath or around it, and step back when it's done. Go back to that image from the start. A 7,600-ton school lifted onto 200 robotic legs, walking down a Shanghai street one careful step at a time. That single image broke a rule that had held for as long as humans have built permanent structures. A building was supposed to be the one thing that didn't move. It turns out that rule was never about physics. It was about imagination. Once engineers stopped treating a foundation as a building's final resting place, the size of the structure stopped being the limit. The only real question left is which building gets to walk next.